first class, in lesson 13, we had an overview of power system stability. Okay. In lesson 14, that is in the last class, we derived swing equation. As we discussed during the very first class, among rotor angle stability, frequency stability and voltage stability, our concern is only rotor angle stability. Rotor angle stability is related to the dynamics of the machine, how the machine rotates. Since synchronous machine rotor is a huge mass, it has some moment of inertia. So we discussed that the equation can be derived as the moment of inertia into the angular acceleration of the rotor is equal to the accelerating power. What is the accelerating power? The mechanical power input minus the back EMF, the power due to back EMF of the electrical power. Okay, so that is the accelerating power, and due to the accelerating power, the rotor accelerates, and hence this equation is known as the swing equation. Okay, so we will focus on this equation to determine the stability of the synchronous machine. So here we are considering the conventional power system where the power system contains mostly synchronous machines and the stability is due to the rotational inertia of the synchronous machine. So what we say? What is the meaning of this? You might know it. I would say in conventional power systems, okay, stability is due to rotational inertia. Due to the inertia, the huge mass which is rotating has some kinetic energy. So by the time you change the input in terms of water or steam, the kinetic energy provides the required electrical power. Okay. Now the question is, in modern power systems, when you have renewable integration, we have wind machines which are small, much smaller comparison to this turbo and hydro generators. Also, we have PV plants where there is no rotational system. Okay. So the question is, who will provide the stability? Also, in microgrids where we do not have such huge machines, which part will provide this stability? Okay. So that is the question of the current research for the new power system. But in conventional systems, currently also we have lots of thermal power, which more than 80% goes into the grid. So no stability problem so far. So today's class in lesson 15 we will discuss small signal stability. That means when load changes are small, there is no fault. Okay. So after this class, for the next 3 classes we will discuss transient stability. Okay. Closely related to the swing equation, which is related to dynamics of the machine, is the power angle equation. It says how the machine will, synchronous machine, supply electrical power. Okay. The power angle equation is given by EV by x sin delta from the synchronous machine. Okay, for the salient pole generator, cylindrical generator. For the salient pole generator, we have two XS. Right? Two reactances XD and XQ. In gate also sometimes they ask you have certain process by which you find the voltage regulation for salient pole machines. Okay. So for our purpose we will use the simplified equation. Okay, only the XD. Okay. Why there are two reactances in case of salient pole machine?
Air gaps non-uniform pressure.
The air gap is smaller at the point of pole faces, whereas in the quadrature axis 90 degree to that, between two poles the angle is 180 degree, so half is 90 degree. So within that 90 degree space the air gap becomes very large. So that's why only one reactance if you consider, the results are not accurate. So we go for two reactances. It's actually not two reactances, it's actually so many reactances. Okay. So this is cylindrical, which we will consider. And finally we will consider one SMIB system. What is SMIB system? I have told you. When we study stability, we consider a SMIB system. What is a SMIB system? Single machine, infinite bus. Single machine connected to the infinite bus. Okay, that system we will consider. So all of you draw this single machine infinite bus system. You have a single synchronous generator connected to the infinite bus. The bus voltage is fixed, EB or VB, whatever, or V. It's also known as infinite bus, right? Because the voltage is constant, voltage and frequency is constant. Now this generator has a reactance XD. We just discussed EB by XD sin delta. It is the reactance of the generator, right? Because of the winding. The generated voltage inside the generator is EG at load angle delta. But because of the reactance, the terminal voltage reduces to VP, the terminal voltage. VT and EP must be same here. And this is the transmission line reactance. This is the transmission line reactance. Right? So when I write power angle equation for this single machine infinite bus system, what should I write? I should write EG, VT. No, I will write EB. Okay, EG, EB. If I consider both EG, generator voltage, and the terminal voltage divided by the reactance. What are the reactance in between? XD plus XC. Okay, depends. So that means the generator voltage into terminal voltage divided by the reactances into sin delta. That is the power angle equation. Now, since it is a sin delta, see, it is simply a sine curve. So it looks like this. Sine curve, right? So this angle is also, this curve is also known as power angle. Clear? So what is the significance of the power angle curve? What is the significance of the power angle curve? If you see this is the stability limit, this point. Okay, beyond this it has negative slope, hence it is unstable. So you can only operate on this side. That means delta must be less than, what is the value of delta?
Less than equal to 90.
Delta must be less than equal to 90. That is the theoretical steady state stability limit. Okay. But practically it is around 30 degree. Maximum delta max is around 30 degree. Practically. Okay. Now how the machine responds when the load changes? How the machine responds when the load changes? Suppose initially the machine is operating at a load of T0 and there is a increase in load of delta P. When I say increase, I am talking about small increase, in steps of small increase, because we are considering steady state stability. So in that case, the load angle must increase by delta delta. Okay. So because of this increase in delta delta, the power increases further. Okay, it goes to some other point in the power angle curve. Right? Now as you know, it doesn't do that at once. It oscillates. It oscillates around that point known as hunting. Okay. And here we are simply mathematically representing some physical phenomena. So physically the rotor shifts with respect to the rotating magnetic field. That is the physical shifting. Okay. And the shifting takes some to and fro motion, and therefore it is known as hunting. Okay. So this is how power angle equation explains how the machine meets the load demand, either increase or decrease. So you can say that whenever the machine is operating for small changes in load, the machine follows the contour of power angle curve, and it operates well below the 90-degree limit. Okay, and I have told you in the very first class, it is not possible for the machine to operate above 90 degree, but during fault, okay, it goes beyond 90 degree, but it comes back. Now it is the capacity of the machine to come back after crossing 90 degree that makes it more stable. So there is a limit also. To some angle it can go, beyond that it cannot go. So that angle is known as critical clearing angle. So before that the fault should be cleared. Okay, as in your lab you have plotted 3 curves. In one sustained fault, the load angle continuously increases. It is unstable case. Okay, we'll see that. Next. So what exactly is small signal stability? As I have told you, the ability, right on the first line, ability of the system to maintain stability under minor disturbances is called small signal stability. This is also called small disturbance stability or steady state stability. After the disturbance disappears, stability is assured if the system returns to the original state. Original state means it settles to a new angle, new load angle. It settles to a new load angle. Okay. So, since the disturbance is minor, we can linearize. So, instead of the power angle equation, we can also use swing equation in this case. Swing equation is for, see, both power angle equation and swing equation represent the same machine. So whatever result we should get from the power angle equation, we should get also from the this swing equation. Okay, but for that we have to linearize it. Okay, for a SMIV system, let the generator be operating initially at a state angle delta 0, as we saw in the last figure. Okay, supplying power P is 0. Okay, we saw that at delta 0 angle it was supplying power P is 0. Under steady state, PM is equal to P is 0. Right? Under steady state, whatever mechanical power input is coming because of the water power or because of the steam power. Any problem? Because of the water power or steam power, the whole power goes to the electrical load. Okay, we are assuming lossless system. Now, if the electrical power is changed by a small amount delta P, the torque angle also changes by delta delta. Okay? Okay? So after using this linearized formula here, okay, we get this equation. Note that moment of inertia into acceleration of the machine is equal to accelerating power, and this accelerating power has resulted from load change. This accelerating power has resulted from the load change. And why there is a negative? Why it is negative? Why it came out to be negative? Load increase, decelerating power. Load decrease, accelerating. That's why it is negative. Okay. Now, this is exactly the solution that generally you see in control system. So we, in S domain, we can find out the solution to be S square is equal to minus Ps by M, or S equals to plus minus J root over Ps by M, where Ps is equal to dou P by dou delta is known as, what is dou P by dou delta? Synchronizing power. Okay, synchronizing power. You might have read in machines, it's known as synchronizing power. Now, should it be very high or low? Synchronizing power should be high or low? If the synchronizing power is low, then the machine cannot follow the load, right? Dou P by dou delta. It doesn't follow the load. The load increases, the machine takes time. Slower. Now if it is very fast, then there is a problem also. So in that case, you are actually overheating the machine, overloading the machine. Okay. If you react to changes too often, then you get tired. Same applies to machines also. Also, if you don't react at all, then there is a problem. So it should not be very high or very low, but it should be positive. It should be positive. That should not be negative synchronizing coefficient. There is nothing like negative synchronizing coefficients. Okay. It's not that load. You need to increase the load and the machine start decreasing the load. It's unstable case. Okay. So it says PS should be positive, right? If PS is positive, S becomes minus J. So in S domain, the pole shifts to left half of the S plane, right? And as you know, for stability in the S domain, the pole must be on the left hand side, or in the worst case, it is on the axis, Y axis, which is known as oscillatory case. So the more left it goes, the less is the hunting. The more it is near to the imaginary axis, more oscillation or more hunting. So we are correlating the physical phenomena with the mathematical S domain. Okay. By the way, why we use S domain?
Differential equations.
Sir, solve करना easy है.
It's more become around algebraic type, right? So it becomes easier. Okay. It's frequency domain. S domain is frequency domain, right? S means j omega, isn't it?
Yes.
Is it? Okay. But if PS less than 0, the roots are real of equal magnitude. Due to the positive real root, the system is unstable. Okay. So PS cannot be negative. It's obvious. Synchronizing power can never be negative. So far we have not included damping. Look at that. Every machine has damping. It's not a resistance. Okay. Human beings, we have also damping. We have some resistance. Resistance is good. Okay. So if you have some resistance, then actually that makes your system stable. It dissipates some energy. Okay. So if you include damping, the equation becomes m d square delta dt square d delta and ps delta. Okay. And this is written of the form s square 2 zeta omega n s omega n square. This is typical linear control system equation. I think many questions yet to be asked. Okay. So what is the solution in this case? So here, so finally, for steady state stability, the swing equation has given you the result which correspond to the linear control system results. Okay, for step input. Right? This result is for step input, step load change. Right? Step load change is small load changes. Okay. No change is there, but for small duration there is a small load change. Okay, it's a step change. So for the step change, okay. So write down this equation for the machine. The equation is s square 2 zeta omega n s omega n square. Roots are minus zeta omega n plus j omega d, and damping frequency is omega n 1 minus zeta square. Okay. This is one of the easiest question to solve in gate if it comes, because you correspond, find out the values and simply compute. It eventually boils down to computation. Okay. Then the final solution is given in this form. Okay. So you know that it goes like something like this, right? Settling time, rise time. So this is the equation. Okay. And because of the load change, because of the step change in the load, there is a small change in the load angle delta delta. Okay. And the machine settles down to that angle. So what we have done, from power angle equation we saw qualitatively how the machine meets the increase in load. From swing equation we saw that swing equation can be linearized. Swing equation can be linearized, and when it is linearized you get this equation, and eventually you get the solution to how the load angle changes. Okay? How the load angle changes. Did you write this? Okay. Write down this. Okay. now we are going to solve the problem. So response time, just write down this equation. The time constant is given by, you know this, right? Time constant is 1 by zeta omega n. 1 by zeta omega n, which in this case is 2 into m by d. Okay, write down this. We are going to solve problem. So it can be observed that natural frequency omega n and damping ratio zeta decreases as h increases, resulting in longer settling time. Okay, it says that when zeta and omega n increases, we have a longer settling time, more hunting takes slowly. Okay. An increase in the synchronizing power coefficient results in an increase in the natural frequency and damping ratio, and hence lower settling time. So the faster the machine responds, results in a lower. There are several problems. Okay. We'll start with question number 3.2.1. Determine the steady state stability limit of the system shown in figure 3.1 if the terminal voltage is 1.0 per unit. What is that figure? Yes, this is the figure. You have already drawn this. Same SMID system, only values are given. Okay. So for this system, find out the what steady state stability limit, which is 90. Delta is 90 degree theoretical maximum, but in this particular case we have to find out based on this reactance. Okay, so it will be E G E B by J 2.0, right? J 2.0. But how to find out Eg? That will be 1 plus J into current, this current, right? Vt is equal to this plus J into current. Similarly, Eg will be Vt plus this current into, right? So you have to find out the current first. What is the current in the line? Get our current. Eg minus by 2. Okay. So for that you need to find out the data. Data what Eg?
Vt 1%.
Vt is given 1.0 per unit. Okay. So find out Vt is equal to, find out. The first part I have shown you. First you need to find out the current. Find out the current. Okay. So here what we are doing? Okay, we find out the current Vt minus the voltage by Vt minus the bus voltage, which is 1 by J. So this is the current. Eg is equal to Vt plus this current into J 1.0, which comes out to be this. Now since Eg delta is equal to Eg cos delta plus Eg sin delta, and delta is 90 degree for maximum power transfer or steady state stability limit. So this cancels out. This is 0. Okay. So therefore you have only this part. So we equate the real part to be 0 and find out theta to be 1.732. Okay. So steady state stability limit we get 0.866 per unit. Okay. Next question. Yes. This will require the swing equation solution, that natural frequency operation and all those things. Okay. Solve it. Read the question, solve it. Those 1 by 4 zeta and omega and 2 zeta, all these things will be required. Okay. Solve it. Question number 2. Okay. For this question, first you need to find out the P max, which is Eg EV by X. Okay. X you can find out from here, this circuit, 0.4 plus parallel combination of these two. From maximum, we have the maximum value. Okay, from there, the question is given how much power is transferred. So we know delta 0 is equal to initial operating angle is 22.54. Okay. Then we find out the synchronizing coefficient, which is dou p by dou delta. So sin delta is differentiation, which is cos delta. So we know. So this is the synchronizing coefficients. And these values we have seen these equations in the slide. So using that you can find out the result. Next question is again the same problem. We find out all this nature of omega and zeta, settling time, delta. That you get the standard equation. What is that? S square plus 2 zeta omega and s plus omega s. So you get the equation and the machine's equation. Compare and find out. Okay. Okay. So the solutions are given. You can check. Okay. And this is the typical swing curve. If you plot it in some software, Scilab or Octave, you can find out the swing curve from here. This is the equation. You see, 8.94 e to the minus 2.11 t. Note that this e to the power minus 2.11 t. What is that? Decrease. That's why this oscillation is decreasing because of this term only. Okay, because of this term. Okay. So because of this only, this oscillation is decreasing. So this is actually hunting. This. Okay. And this is the last one. And this question is a bit involved. So I suggest all of you go through this question. This uses swing equation called steady state stability. It is from NPTEL. It's a very involved question. So all of you go through it. Okay, so with this, we stop here.